Hello everyone and welcome back. In the first video, we looked at the basics of energy efficiency in mobile networks. We talked about energy saving, energy efficiency, power consumption, energy consumption, static measurements, dynamic measurements, and KPIs. In the second video, we move into LTE and look at how 3GPP started addressing network energy saving in a more practical way. The LTE era is very important because many of the concepts that we still talk about today started here. Things like dormant mode, carrier switch off, cell DTX, compensation cells, OAM-based control and signaling-based coordination. The basic idea was simple. When traffic is low, reduce unnecessary radioactivity. But the difficult part is doing that without harming coverage, mobility, service continuity, or user experience. So in this video, we will look at how LTE networks can save energy and why these early ideas became the foundation for later 5G and 5G advanced energy saving techniques. In video 1, we saw that energy efficiency starts with measurement. You first need to understand the network. Where is the traffic? When are the busy hours? Which cells are lightly loaded? Which carriers are underused? How does power consumption change across the day? But measurement by itself is not enough. At some point, the network has to turn those insights into action. In LTE, this meant asking a very practical question. What can the network safely reduce, mute, or switch off when traffic is low? That word safely is important. We are not just trying to save energy at any cost. The network still needs to maintain coverage, mobility, accessibility, and user experience. So the process is something like this. First, measure the network. Collect power, load, traffic, and KPI data. Second, detect low load periods. Identify where and when traffic is low enough to create an energy saving opportunity. Third, reduce radioactivity. This could mean switching off a carrier, reducing common channel power, deactivating secondary antennas, using DTX, or switching off a small cell. Fourth, monitor user experience. Check coverage, QoS, mobility, and service continuity to ensure the energy saving action has not created a new problem. That is the central idea for this video. Use the right mechanism at the right time in the right place. The LTE energy saving philosophy is built around a simple but powerful principle. Capacity demand changes, but coverage must remain. In other words, the amount of traffic carried by the network changes throughout the day. Some areas are busy during office hours. Some are busy in the evening. Some small cells may only be heavily used during specific events. Some carriers may be needed during peak periods but not during the night. Capacity can therefore be adapted. But coverage is different. Users still need to be reachable. Idle users still need to camp on a cell. Mobility still needs to work. Emergency services still need to be available. So LTE energy saving tries to switch off or reduce capacity resources when they are not required, while keeping users reachable and mobile. This is why many LTE energy saving mechanisms use the idea of a coverage layer and a capacity layer. The coverage layer stays available. The capacity layer can be reduced, muted, or switched off when demand is low. In short, LTE tries to adapt capacity to demand while preserving coverage and service continuity. Let us start with dormant mode and carrier switch off. Dormant mode refers to switching off one or more carriers when they are not needed. Think of an LTE base station with multiple carriers. During busy periods, all carriers may be active because the network needs maximum capacity. But during low load periods, one carrier may be enough to carry the available traffic. so the network can deactivate the unused carriers. This can reduce energy consumption because deactivating a carrier may allow parts of the radio chain to be powered down. In some implementations, it may allow a power amplifier to be powered down or completely shut off. The exact savings depend on the hardware design. For example, the behavior will be different if carriers share a multi-carrier power amplifier compared with a design where separate RF paths can be switched off more independently. The key idea is that the remaining active carrier continues to provide coverage and service while unused capacity is taken out of operation. When traffic increases again, the dormant carrier can be reactivated. This is one of the most intuitive forms of energy saving. Do not keep every carrier active if the traffic does not justify it. Another early mechanism is secondary antenna deactivation. This applies in the context of MIMO, where multiple antennas or antenna paths are used to improve performance, diversity, and capacity. During high load periods, the network may benefit from keeping multiple MIMO paths active. But when traffic is low, the network may not need all those layers or diversity paths. So one option is to deactivate secondary antenna paths. This can reduce energy consumption because fewer RF chains and associated components need to remain active. However, this is not free. Deactivating secondary antenna paths may reduce capacity, diversity, or robustness. That means it has to be controlled carefully. For example, it may be suitable when the cell is lightly loaded, users have good radio conditions, and the operator's policy allows a lower performance mode. But it may not be suitable if users are at the cell edge or if the network needs the diversity gain to maintain service quality. So the key message is secondary antenna deactivation saves energy by reducing active RF resources, but it must be balanced against coverage capacity and QoS requirements. The next concept is common channel power control. In a mobile network, not all transmissions are user-specific data. Some channels and signals are transmitted to support basic cell operation, coverage, and access. If these common channels are always transmitted at a high fixed power level, the network may be using more energy than necessary. Common channel power control allows the network to adjust the transmit power of common channels to match the coverage actually required for active users. This is an important idea. Instead of transmitting at maximum power everywhere, the network tries to use just enough power. If all active users are close to the cell or located in areas with good propagation conditions, the cell may not need to transmit common channels at the highest level. Reducing the power can lower energy consumption in the radio unit and power amplifier. But again, this has to be done carefully. If the power is reduced too much, coverage can suffer. Idle users may not detect the cell properly. Mobility and accessibility may be affected. So the goal is not simply to lower power. The goal is to deliver the coverage users need, not more and not less. This is one of the early examples of a more intelligent energy saving philosophy. Focus energy where it is useful. Now let us look at cell DTX or discontinuous transmission. The idea behind cell DTX is to stop transmitting for short periods when there is no need to transmit. During low traffic, there may be gaps where the cell does not have downlink data to send. If the radio continues transmitting unnecessarily, energy is wasted. Cell DTX allows the cell to periodically turn off the power amplifier during these inactive periods. This is important because the power amplifier is one of the most energy consuming parts of the radio chain. If it can be switched off, even briefly, energy can be saved. But to achieve meaningful savings, the downlink channels need to be shut down together. If some signal still needs to be transmitted, the power amplifier may not be able to actually switch off. So cell DTX is not just about creating small gaps, it is about organizing transmission so that the radio can enter a low power state during the gaps. When traffic returns, transmission must resume quickly, so users are not affected. This is a recurring theme in mobile energy saving. Sleep when possible, wake quickly when needed. The next mechanism is cell switch off in a single layer LTE network. Imagine a dense LTE deployment where several neighboring cells provide coverage and capacity in the same area. During busy periods, all cells may be active, but during low load periods, some cells may be lightly used or almost unused. In this case, one cell can be switched off to save energy. The neighboring cells then compensate by adjusting their coverage or capacity. The cell being switched off is often called the energy saving cell. The neighboring cells that maintain service are compensation cells. This is easy to understand in theory, but it needs careful coordination in practice. User connected to the switched off cell may need to be handed over or later reselect another cell. Neighboring cells may need to adjust power, antenna, tilt, or resource allocation. The operator must make sure that no coverage hole is created. The key message is switch off what you do not need but keep users covered. Single layer cell switch off demonstrates one of the main LTE energy saving principles. Reduce the number of active cells when traffic is low, but use neighboring cells to preserve service. Another important scenario is overlay coverage. In an overlay deployment, a wide area macro layer provides basic coverage, while smaller cells provide extra capacity in hotspots. For example, a macro cell may cover a broad area, while smaller LTE cells provide additional capacity in a shopping center, office district, train station, or other high demand areas. During busy periods, the capacity cells are useful. They offload traffic from the macro layer and improve local performance. But during low load periods, those small cells may not be needed. So the LTE energy saving idea is to switch off the smaller capacity cells when demand is low, while the macro layer continues to provide coverage and basic service. This approach is attractive because it separates coverage from capacity. The macro layer remains available so users stay connected and reachable. The smaller cells are activated only when extra local capacity is needed. Again, the key is control. The network has to decide when to switch off a capacity cell, when to wake it up, and how to ensure that users are moved smoothly between layers. This is a very important concept that continues into later network design. Use the right layer for the right purpose. Now we come to an important operational question. Who decides when to switch things off or on? There are two broad approaches: OAM-based control and signaling-based control. OAM stands for Operations Administration and Maintenance. In an OAM-based approach, decisions are made centrally or semi-centrally using configured policies, thresholds, statistics, and planning rules. For example, the operator may configure certain cells to enter an energy-saving mode during known low traffic periods, such as night time. The decision may use historical patterns, KPI data, and operator-defined rules. This approach is useful for planned and policy-driven energy saving. The second approach is signaling-based control. Here, neighboring E-node Bs exchange information and coordinate more dynamically. They may share information such as load, thresholds, coverage needs, cell status, activation or deactivation requests, and whether a cell can compensate for another cell. This allows the network to react more flexibly to actual conditions. For example, an energy saving cell may decide that it wants to enter dormant mode, but the final decision may depend on whether neighboring compensation cells can maintain coverage and handle the traffic. So OAM-based control is more centralized and policy-driven. Signaling-based control is more neighbor-aware and dynamic. In practice, both approaches can be useful, and operators may use them together. At this point, it might sound simple. Just switch off unused carriers, antennas, or cells. But in real networks, it is much more complicated. The network must preserve coverage. If a cell is switched off, the operator must avoid coverage holes or weak signal areas. It must avoid dropped calls and session failures. Users already connected to the network should not suddenly lose service because an energy saving policy was too aggressive. It must manage mobility and handovers. If users are moved between cells, the process needs to be smooth. It must avoid ping-pong behavior, where cells repeatedly switch on and off because the thresholds are poorly designed. It must support idle users. Even when there is no active traffic, users still need to camp on the network, receive paging, and access services when required. It must maintain emergency service availability. Energy saving must not compromise public safety or emergency access. And finally, the network must react quickly when load returns. This is why energy saving is a balancing act. On one side, we have energy savings. On the other side, we have network performance, coverage, mobility, QoS, and reliability. The key is intelligent control, coordination, and real-time awareness. The early Release 10 work introduced the main principles and use cases for LTE and E-UTRAN energy saving. Release 12 then studied E-UTRAN energy saving enhancements in more depth. The Release 12 study looked at how these earlier concepts could be coordinated more effectively. Three scenarios are especially important. First, inter-E-node B energy saving, where neighboring E-node Bs coordinate so that some cells can be switched off while others compensate. Second, a single compensating E-node B scenario where one E-node B or cell provides compensation for a switched off neighbor. Third, multiple compensating E-node Bs where several neighboring E-node Bs share the compensation responsibility. This is important because energy saving is not just a single cell decision. A cell may want to switch off, but the network has to understand the impact on neighboring cells, coverage, load, and user experience. Release 12 helped move the thinking from isolated switch-off decisions towards better coordination across the E-UTRAN. The aim was to maximize energy savings with minimal impact on users. So what did LTE teach us? First, energy saving is possible. LTE showed that carriers, antennas, transmissions, and even cells can be reduced, muted, or switched off under the right conditions. Second, switching off is not enough. You need compensation. If one cell or carrier sleeps, something else must maintain coverage and service. Third, neighbor awareness matters. Cells do not operate in isolation. Load, coverage, interference, handovers, and user movement are all connected. Fourth, KPI monitoring is essential. Operators need to track energy savings, coverage, drop rates, QoS, utilization, user experience, and reactivation behavior. Fifth, fast recovery is critical. Traffic can return suddenly. The network must be able to wake resources quickly before users notice a problem. These lessons carry directly into 5G. In 5G, energy saving becomes more granular, more dynamic, and more closely linked with radio design, scheduling, bandwidth parts, carrier management, beamforming, and eventually AI-assisted optimization. LT gave the industry the early building blocks. 5G takes those ideas further. That brings us to the end of this LT focused video. In this episode, we saw how LTE networks save energy using mechanisms such as dormant mode, carrier switch off, secondary antenna deactivation, common channel power control, cell DTX, single layer cell switch off, and overlay coverage with capacity cells. We also looked at OAM-based and signaling-based control and why Release 12 studied E-UTRAN energy-saving enhancements in more detail. The most important lesson is that energy saving is not simply about switching things off. It is about switching off the right resources at the right time, in the right place, while maintaining the right coverage, mobility, and user experience. In the next video, we move from LTE to 5G NR. This is where the story changes. 5G was designed with a leaner air interface, better sleep opportunities, bandwidth parts, more flexible carrier management, and massive MIMO. We will look at why 5G can be more energy efficient by design, even though 5G sites can consume more absolute power. So, in video 3, we will explore how 5G NR moves beyond LTE energy saving and creates a more granular and dynamic foundation for energy efficient mobile networks. Thank you for watching, and I hope to see you in the next part.